Hello and welcome to TidyX episode 57. TidyX is a screencast where we go through and explain how our code works. My name is Ellis Hughes, and you can find me on Twitter at Ellis_Hughes.
And my name's Patrick Ward. You can find me on Twitter at OSPPatrick. And you can find TidyX on Twitter at tidy_explained. Or you can email us tidy.explained@gmail.com. Open up a issue on the GitHub repo for things that you want to see. And like and subscribe to the YouTube channel, and maybe leave a comment down there if you'd like.
Yeah, that'd be awesome. We'd love to hear from y'all. Love to hear what you're thinking of the series that we're doing. You can put in requests for new series. So speaking of, this is episode, 4 or 5?
Maybe 5 of our classification model series on pitchfx data.
Yeah, so we've been, quote, hired by the Fantasy Football League, or not football, no. Baseball. And we are going through and classifying pitches using different algorithms, and we're going to try to figure out which is the best one to be using.
Yeah.
And so this week we decided, the last couple of weeks we've been doing kind of tree-based algorithms. So we did random simple decision tree, random forest. Last week we did XGBoost, and this week we're going to go on different route.
Yeah, we're going to do a Niave Bayes classifier this week.
So what is a Niave Bayes classifier?
Yeah, so for anybody who's kind of familiar with, oops, what did I just do?
Nobody can see it still. Yeah.
I just clicked on something and blew up my computer. For anybody who's familiar with Bayes' theorem, it's a way of dealing with conditional probabilities. And in this case, unlike the typical binary classification examples you might see if you were to Google Bayes, we're going to have multi-classes, right? So we've got 9 classes, and we're going to use the empirical data in our training set to build a model based on the same the same types of features. I think it's 10 features that we've been using for the other classification algorithms. And we're going to use those features to try and predict the probability of pitch type given the conditioning on those 10 features, right? Mm-hmm. And it's naive because one of the reasons is there's an assumption of independence, which really doesn't hold here for our data, actually. These aren't independent observations. We have, I can't recall how many rows of data we have.
26,000 or something like that.
Exactly.
That's a lot.
26,000 with thousands of those rows probably being, specific to different pitchers, or at least hundreds of those rows being specific to different pitchers. So they aren't really independent because they're probably, we have a reason to believe there's probably some level of autocorrelation. So, Kershaw probably throws very similar to, his fastball is probably similar to however Kershaw is going to throw a fastball, and another pitcher is going to be similar to, Madison Bumgarner is going to be similar to himself. That being said, Niave Bayes classification, or Niave Bayes classifiers tends to do relatively well, even if the independence assumption is violated. So we're going to try and play with that today and see what we get.
Alrighty. So Patrick is sharing his screen this week, so I will make his screen large now and make our faces a little bit smaller, and we'll get going.
Okay, so this whole top part is the load the data and the clean the data and the prepare the data that we've done, 5 straight times. So we're gonna give that a run for a second and let that go.
So that is just loading in all the data, removing some extra pitches that are super rare, and subsetting down to keep only the records or the columns that we care about. So the pitchfx data that we think has an impact.
Correct. Okay, so now we'll scroll down. I've been kind of keeping all of our models in series, so I'll scroll to the bottom to get down to the Niave Bayes classifier section. We'll put this into a markdown with just the Niave Bayes classifier so that it's not all as cluttered as the housekeeping that I do. So the first thing I do here is I'm going to convert the pitch type to numeric. We did this with the XGBoost model as well. So I'm going to convert it to each of the pitch types to a numeric value from 0 up to 8, because we have 9 total pitch types. So I'm going to do that for the training set. I'm going to do that for the testing set. And just a quick peek to make sure the diagonal should be 100% accurate. We have each pitch type is now identified by a value.
Sweet.
I'm going to load the E1071 package, which is a machine learning package that has a number of different machine learning algorithms for it. I never knew where the E1071 came from, but Ellis, you have a
so I've heard that is the name of like the classroom at MIT. I think it was MIT that this was developed at, or either the package or the SVM algorithm. So I think that's lore. I don't know how accurate that actually is, but yeah, E1071 is definitely a unique name. So I'm assuming there is a unique story behind it, and that seems to line up with it.
And so we're going to use from that package this Niave Bayes function to run our Niave Bayes classifier. So let's take a quick peek. And here we are. There's our Niave Bayes classifier from the E1071 package. So we see that this computes the conditional a posterior probabilities of a categorical class variable given independent predictor variables using Bayes' rule, which is what we explained at the top of this of the screencast.
Yep.
And so down here we see our arguments. We're going to need to pass it an x value, which is the numeric value specific to the categorical variables, which is what we just created, and then our class of, or sorry, the x variable is going to be our x values, our independent variables.
What's going to be predicting.
Correct. And then the y variable is the classes. And I guess we could have done this by formula. I've never known that. I've never actually done that.
Surprise.
So, yeah, surprise. This is why you do question and then question mark and then the function to find these things out. This is the typical way that I've always done it, though, is to just feed it the x and the y variable, or the independent and dependent variables. So our x variable is going to be trained cleaned, and we're just getting rid of pitch type and pitch type num, obviously, because those are the dependent variables that we're trying to forecast. And then our y variable is selecting the pitch type num, because that's what we care about. And we're going to run this model. It shouldn't take too long to run, and it's already done.
That's a lot faster than some of the other algorithms that we've used so far.
It is, yeah. And so we could look at what sort of variables are available for us within this model. So if we do names, fit, NB, and we can see the different values, the different variables within this model. We can, of course, run the model and get all that information returned back to us. So we can scroll up here and we can see the a priori probabilities. So these would be our priors based on each of the relative pitch types, et cetera, et cetera. And then we have our different tables for conditional probabilities specific to, these are our x variables, our independent variables that we fed into the model, the 10 variables. Cool. Okay, so we've got a model. Ellis, you want to talk us through putting the predictions back into the original data set?
Yeah, because now that we have a model that can actually make some predictions for us, we need to see how well it's doing. So we're going to throw that, we're going to test that against our test data set. So use the function predict. The first argument is the model object that we created, which is a fit.nb, and we throw in the new data, which is test cleaned, which it has not seen before. So this is going to be a true representation of how accurate our model is on data it hasn't seen before. And we say, hey, give us the type raw, which is telling the predict function to return a matrix of all the different predictions that it gives us. So it's a really nice way to kind of take a quick look at what the model is thinking. So like if you in episode 50 or 51, we had a Shiny app that was showing the predictions of different Palmer penguin species that you might be able to look at. And so here would be a way to, like, I threw this pitch here. It went at 87 miles an hour, but it had very little movement in the X and Y axis. So the model would go, it wasn't very fast, but it didn't have a lot of movement. So it might have been a fastball, but it also could have been a different type of pitch as well. So you can kind of look to see what the model's actually thinking when you throw that. So that's a reason why you might want to do that.
So here's what the head of that looked like, right? So pitch number 3, let me just get our quick table. We'll put the names back in here in a second. Pitch number 3 was a 4-seam fastball, and there was a 64% probability that that's what it had classified, and there was still a 28% probability that it was pitch number 5, which is FT, which is a different type of fastball. Yeah. So things like that, like we did with that random forest penguins classifier, can be kind of cool for the domain experts to pluck around with, and it helps them kind of look at, well, what different types of probabilities might this have been? And that might help them explain things. Obviously, it'd be really weird if there was a high probability of it being a 4-seam fastball and a high probability of being something totally different, like a knuckle curve. That might make them raise questions and think about
they'd be like, what is your model even doing?
Exactly.
And so this is a way to like interrogate your model and understand what's going on with that.
So that's the head of the raw data. So now we'll pick up here at line 688.
Yep. So now we're going to convert it into a data frame. So it comes out of predict as a matrix, which is an object that is super helpful, has a lot of applications here, but it means that everything has to be the same type, which we don't want. We want to be able to add in the actual names of the pitches that we're predicting here. So what we're going to do is we're going to say, hey, predict, let's convert the output here into a data frame at line 688, and then we're going to set the names. So before we had those numeric, the numbers that we previously just had to go up and figure out, but we actually know that those numbers represent the levels that we want here. So what we're going to do is you can use the function set names to set the names of each of the columns to be the actual pitch type that we predicted, and then do a round across. So now that we've got the names of all the pitches, we're going to throw it into a mutate, and we're going to round each column to 3 decimals. Once again, that's an aesthetics thing just to make it easier to view. So we're going to run that all.
So that's already done running.
So then if we do another head on preds,
you can take a look at it. And so now you can see some of those values that, where it was such an extremely low probability that it's actually feeding it back to us in scientific notation. The model just drops that all the way to 0 because at whatever 13 significant digits or whatever that was, it's not even meaningful.
Yeah,
so
it's
this
not
first line, this first line, the discussion is really between the 4-seam fastball, which it's suggesting with a high probability that that's what it was, pitch FT, and then there's a small probability about
sinker,
right? 8% that's a sinker, or sinker.
Yeah, I think a sinker.
Okay.
One of these days we'll actually know, like, oh, this is this. All right, so now we're going to actually get, like, what is the actual prediction here? So we're going to call factor. So we're going to convert it back into a factor eventually. So this is kind of a weird nested situation here. So the logic is a little bit strange. So we're going to ignore for a moment line 695 and look at 696. So what we're going to do here is we're going to call the levels of test clean pitch type. So that'll tell us which pitch type. It gives us a vector of the different pitch types that are available. And then we're going to, using vectorization, in the next bit of the chunk max.call preds ties method first. So this is going to say, okay, which of the columns for each row is the highest value at? And then use that to. This is just a very complicated piece. It is.
This is not my most elegant writing. This is pretty sloppy. But it's basically what it's doing is it's looking horizontally across each row, and it's saying, hey, where's the highest value? Oh, here it is. Well, whatever row name that is, drop it into a new column. So it's going to say FF here. Here it's going to say FT. Here it's going to say FT. So it's basically saying, hey, look across the different levels of test clean pitch type, which are these row names, and look at the max across the columns. And it says, if you find the max, just go ahead and deposit that level across the names there into a new column. So
that is a much more elegant way of saying it.
It's an elegant way of saying some very sloppy code. Sloppy code.
What is going on? No, I think I wrote this.
But it's a handy piece of code, but it's not nice. And if you have a better way of doing this, obviously this is very base R, so I think
there's probably a better way.
Something like this a couple years ago and just kept using it and got lazy to try and find a better way. So if you have a better way in base R on the YouTube channel, throw it in there and we will show it next time.
Yes, we'll add it in. So this is how we get the actual predicted pitch. So we add a column, pred pitch, and this is our prediction.
We'll run that. And now
we also added the original pitch type as well because we have that information. So now we're able to have, these are the predictions of the model, the percents, the actual called prediction based on what is the maximum percent likelihood, and then what is the true, based on the data, true pitch type.
So row 1 is fascinating, right? Because the predicted pitch type was 4-seam fastball at 64%. 63.9%, but the actual pitch type was FC, which really only had a 0.1% probability from our Niave Bayes Classifier. So that's pretty cool. So we can check these results. I'll just make a note here that this is going to be this is our
confusion matrix,
right? So we're going to make a little table here of taking that new data set that we just created. We're going to put the original pitch type on the vertical, and we're going to put the predicted pitch type on the horizontal. You can name these directly. Sometimes I just name them. I put in the 2 vectors, and then I name it outside of that with this little DNN argument, and you just pass it the names that you want to see. So here we're going to have observed, again, on the horizontal and predicted on the vertical, observed on the vertical and predicted on the horizontal. And if you recall some of the confusion matrices of the models that we had produced before, they tended to look a little bit cleaner than this. Mm-hmm. And so let's just take a look.
Bit more like scattered all over.
Yeah, we have a lot more activity going on, like especially here, slider, it really, and I guess it got, 1,456 correct. But we have a lot of like action here, which is kind of weird. So, and a lot of action here in the 4-seam fastball, which is the highest class, remember. And we usually do a pretty good job in other models with predicting that at, I think, over 90% accuracy, mainly because it is the highest class. And so, when you have classifiers, sometimes the safest bet is to guess on the highest class. But let's take a look at our accuracy of this model. So we're going to sum. So we have this table, and we're just going to first say, hey, let's go ahead and sum up the diagonal. I don't need the names. Let me get rid of that. That's kind of sloppy. Okay, that's much cleaner. So we're going to say, hey, sum this diagonal, which are the diagonal, if you remember from a confusion matrix, are the true positives. So basically, we observed a changeup and we predicted a changeup. We observed a cutter and we predicted a cutter. So we're going to sum up the true positives, and we're going to divide by the overall total data set that we're predicting on. In this case, the number of rows or number of observations within the pred data set. And you can see that we're like 10% worse overall accuracy than the prior models that, tree-based models that we had, which were checking in around like 72%. And I think the XG boost was like 73 or 74% once we tuned it.
I think it was like close to 76. But either way, they're substantially better than this guy here. This model.
Yeah. But we are looking at overall accuracy. So, Ellis, why don't you walk us through, again, this is something that we've done in the previous models. Why don't we walk through talking about within pitch type accuracy?
Sure. So now we're going to figure out, basically we're going to convert this table here into a long format for us to be able to then look at what is the percent accuracy within each correct pitch type. What is the accuracy type? So what we're going to do is we're going to take preds, we're going to throw it into a count. We're going to go, hey, give us the count for each pred pitch and original pitch type. So then it's going to give us a number of every time the observed type was CH and the predicted type was CH, it'll give us a number. Then every time the observed was CH and the predicted type was CU, it gives us a number. So it's, exactly what we did before, right? And now we're going to group by original pitch type. and go, okay, what are the actual number of pitches? So group by original pitch type, summarize n. So n is going to be the sum of n. So what are the total number of pitches for that pitch type? And then what are the total number of matches? And so there we're going to do a weird little sum, which is going to be sum if else. So if the pitch type is the actual pitch type, return that number. Otherwise, return a 0.
Yep.
And then we're going to calculate our within accuracy. So within accuracy is the total number of matches, so the total number we guessed correct, divided by the total number of pitches for that pitch type, for that class. And so let's quickly run that.
Okay.
All right, so here we go. So like changeup, which is was it changeup?
Four-seam fastball was our highest.
Yeah.
Is the highest class, right? And we were usually getting like 92%, so 91%.
Got to 92.
Yeah, so we lost about 6%, right? We're down to like 86% accuracy. We got 4,843 hits out of 5,642 four-seam fastball observations.
Mm-hmm.
So we got a little worse there, but the Niave Bayes model is sort of partitioning some of these classification outcomes to different classes now, whereas the tree-based models were a little bit more bullish on the highest observed class, the largest class.
Exactly. So like, for example, the slider here at 2,323 was a within accuracy of 0.627 also. That's lower than our tree-based algorithm as well.
Yeah. So it's a relatively simple model. It didn't do as well. In some of the different groups, it might have done a little bit better.
Yeah, I think the FS...
At the expense of four-seam fastball. But so don't really know what to think of that. I guess we'll look at it more closely when we start comparing these models. We probably have one more model to build maybe, and then we can get into that. But yeah, it is kind of interesting to like look at this and think about it, and maybe think about ensemble models and comparing some of the predictions of these things, or utilizing the prediction of some of these things in order to help us get a little closer to the ground truth. Right?
So yeah, I think this would be a good candidate to mix with our XGBoost model. So XGBoost is an ensemble model on its own, but there is a way for listeners that you can start combining multiple algorithms that you've trained independently to then bring them together and aggregate their predictions as well. So you can like aggregate aggregations and with their powers combined, it's even more wisdom of the crowd. And they're just looking at things in different ways. And so we'd consider this a not good model, but it's capturing information that the tree-based models weren't.
Correct.
And so this might help us bump up the accuracy of the overall model, because even though this model itself isn't very good, with its powers combined with the other models, it could be better.
Yeah, and we could try and combine predictions from different models, and you can weight the models based on how accurate they are, or how valid they are, and things like that. So maybe that's something we can look at. I know we have probably one other model to try out, but that was kind of a quick and dirty run through of Niave Bayes classifiers, and I think with that, we'll probably call it.
Yep.
We'll get into something next week.
Yeah. Once again, thank you all so much for joining us. We love talking about this. Please leave a comment down below with any questions, comments you have. My name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name's Patrick Ward. You can find me on Twitter at OSPPatrick. And you can find the both of us on Twitter through the TidyX Twitter handle at tidy_explained. You can hit us up on Gmail, tidy.explained@gmail.com. You can like and subscribe to the YouTube channel and drop some questions or comments. If you have a more elegant way of sorting out the identifying the row with the highest value or the column with the highest value, feel free to post it there, and we'll talk about that. Or you can open up an issue on the GitHub repo if there's kind of something that you're curious about or would like to see us cover. I think we have 2 or 3 issues that I've opened myself. So feel free to jump in. I've sort of started the trend, so jump in.
All right. Thank you all so much, and keep on exploring your world.